As of this morning, May 18th, 2026, a transequatorial coronal hole spanning the full north to south diameter of the Sun, one of the most geometrically potent configurations our star can produce, is driving a high-speed solar wind stream directly into Earth's magnetosphere at velocities approaching 700 kilometers per second, and NOAA's Space Weather Prediction Center has confirmed that geomagnetically induced storm conditions at the G1 level are already being registered, with G2 moderate storm thresholds within reach before this day is over. The KP index, the planetary index that measures the disturbance in Earth's magnetic field on a scale of 0 to 9, reached 5 this afternoon, the threshold at which engineers who manage high-voltage transmission infrastructure begin paying very close attention. The instruments are not speculating. The instruments are measuring. If you rely on this channel for science that is grounded in verified data and explained with honesty, subscribing ensures that none of this reaches you late. Every event covered here is anchored in official monitoring data, not projection. This work depends on the audience that values it. Every figure in this script was drawn from official scientific and governmental sources. NOAA's Space Weather Prediction Center, NASA's Solar Dynamics Observatory, Space Weather, COM, Space Weather Live, Earth Sky, and peer-reviewed research on geomagnetically induced currents and grid vulnerability. But official sources are not infallible, and neither is the human process of reading them. Before any decision is made, whether personal, professional, or otherwise, verify independently through the official channels. The sources are listed. The data is public. The responsibility to check belongs to all of us. But that is not even the complete picture. What is happening above Earth's atmosphere right now is not simply a matter of auroras appearing over Seattle, or GPS signals stuttering for a few minutes, or HF radio operators losing their frequency windows. What is happening right now sits at the intersection of two converging forces. A sun operating at the energetic peak of solar cycle 25, which has already surpassed every forecast issued at its beginning, and a global electrical grid infrastructure that was engineered in an era when no one believed a star 150 million kilometers away could collapse a power system serving millions of people within 90 seconds. That belief was shattered in 1989, and what the monitoring agencies are watching today is a direct reminder that the system which failed in 1989 has been rebuilt, expanded, digitized, and made more dependent on electromagnetic stability than at any previous point in human civilization. The transequatorial coronal hole that is facing Earth today is not a minor feature. It stretches from the Sun's northern hemisphere across the solar equator into the southern hemisphere, a configuration that space weather researchers classify as among the most effective producers of sustained high-velocity solar wind. It is not firing a single burst, it is streaming continuously, and it has been doing so for more than 72 hours. To understand what is moving through space toward this planet right now, it helps to begin with the structure of what a coronal hole actually is. The Sun's corona, the outer atmosphere, visible only during a total solar eclipse as the faint, ghostly halo that reaches millions of kilometers into space, is a region where the Sun's magnetic field normally curves back on itself, trapping hot plasma in closed loops. In a coronal hole, those magnetic field lines do not close. They open. They extend outward into the heliosphere like open nozzles, and through those open nozzles, solar wind escapes at velocities that dwarf what emerges from the quieter regions of the solar surface. A standard slow solar wind stream travels at roughly 400 kilometers per second. From a large coronal hole, particularly one that spans both hemispheres, that figure climbs. NOAA's classification of high-speed streams from coronal holes places their velocities between 500 and 800 kilometers per second. What is being measured today is at the upper portion of that range, 700 kilometers per second. To put that number into the scale of something a human mind can hold, at 700 kilometers per second, the solar wind particles striking Earth's magnetic shield are covering the distance between London and New York in approximately 9 seconds. Not 9 hours, not 9 minutes. 9 seconds. That is the speed of the invisible river of charged particles currently pressing against the outer boundary of the only magnetic protection this planet has. And here is where this account becomes genuinely significant. A coronal hole stream alone, even one this large, even one this fast, would not necessarily be the most alarming story of this week. What elevates the situation is the compound nature of the current solar environment. On May 16, 2026, just 2 days ago, active region AR4435 produced an M2, zero solar flare, a moderate class event powerful enough to trigger a minor radio blackout. AR4436, a neighboring active region on the same solar disk, produced an M1, 9 flare on the same day. 4 M-class and 8 C-class flares were recorded in a single 24-hour window. The M1, 9 event from AR4436, was associated with a coronal mass ejection, a CME, that is now traveling through the inner solar system toward Earth. According to the 3-day forecast from Space Weather Live, The arrival of that CME is expected to deliver a glancing blow sometime today or into May 19th. Even a glancing blow from a CME arriving on top of an already active high-speed stream compounds geomagnetic conditions in ways that a single source cannot. The two phenomena interact. The CME's shockwave travels through a solar wind environment that is already disturbed, already compressed, already pressing harder against the magnetosphere than it does during quiet periods. The result is the kind of layered, sustained geomagnetic disturbance that engineers and space weather forecasters find most concerning. Not a single sharp spike that resolves quickly, but a prolonged pressure event that gives geomagnetically induced currents time to accumulate in long-distance transmission lines. That word, accumulate, is the one to stay with. Geomagnetically induced currents, the phenomenon abbreviated as GICs and sometimes described in technical literature as the silent killer of grid infrastructure, are a direct consequence of what happens when Earth's magnetic field is disturbed by solar wind. Faraday's law of electromagnetic induction, first described in 1831, foundational to every electrical generator ever built, states that a changing magnetic field induces a current in any conductor within its range. Earth's magnetic field is a conductor's environment. When a geomagnetic storm warps and oscillates that field, it induces currents in every long conductor on the ground. Pipelines, railway lines, undersea cables, and most critically, the high-voltage transmission lines that carry electricity across continents. These induced currents are not alternating current, they are quasi-direct current. And high-voltage transformers, the enormous irreplaceable nodes that step voltage up for long-distance transmission and back down for local distribution, are engineered to operate with alternating current. When direct current enters a transformer, it saturates the magnetic core. The transformer overheats. In minor cases, it trips offline and can be reset. In severe cases, the core is damaged beyond field repair. In extreme cases, the transformer fails permanently. A failed high-voltage transformer is not a component that can be pulled from a warehouse shelf. These are custom-engineered pieces of infrastructure that weigh between 100 and 400 metric tons, are manufactured by a small number of specialized facilities worldwide, and carry delivery lead times that currently range, depending on specifications and supply chain conditions, from 1 to 4 years. This is not an estimate. It is a manufacturing reality documented by every major grid operator and cited in NOAA risk assessments, USGS vulnerability analyses, and the Lloyd's of London risk modeling that has assessed Carrington-class event damages at between $600 billion and $6 trillion in the first year alone. The system is not inactive. It is accumulating. And now consider where we are in the solar cycle. Solar cycle 25. The current cycle was forecast at its inception to be a moderate, perhaps slightly below average cycle. Those forecasts were wrong. By August 2024, the smooth sunspot number had reached 157, well above the predicted maximum. The sun is operating at or near peak intensity right now in 2026, and while the peak of activity is passing, severe geomagnetic storms are not constrained to solar maximum. The 1859 Carrington Event, the most intense geomagnetic storm in the entirety of the recorded instrumental record, occurred during a solar cycle that by most measures was considered unremarkable in its overall activity. What made 1859 extraordinary was not the cycle, it was the geometry and the timing of multiple events interacting. That same dynamic, compound solar events, coronal hole streams coinciding with CME arrivals, is what the instruments are registering today, at a lower level of severity, but within the same family of behavior. This is not a hypothesis. This is documented in the geological record, in the ice core record, in the historical instrumental record, and in the physical systems that space weather agencies have been monitoring with increasing precision for the past 3 decades. It is worth pausing here at the midpoint of this account and grounding what has been established in a moment that already happened. A moment where the theoretical became catastrophically real, where the science was not a projection, but a lived event experienced by millions of people who had no warning and no understanding of what had struck them. The date was March 13th, 1989. The location was the province of Quebec, Canada, and the event that unfolded in the early hours of that morning remains the most consequential grid failure caused by a geomagnetic storm in the history of the modern electrical age. At 2:44 in the morning, Eastern Standard Time, operations on the Hydro-Quebec power grid were entirely normal. A generation load of some 21,350 megawatts was being managed. Tens of thousands of people were asleep in their homes. Within seconds, a large impulse in Earth's geomagnetic field, the result of coronal mass ejections that had left the sun on March 10th and March 12th, preceded by an X-15 class solar flare on March 6th, sent a surge of geomagnetically induced current through the province's transmission network. 7 protective relay systems activated in sequence, 5 high-voltage transmission lines from James Bay tripped offline. 9,450 megawatts of generation capacity vanished from the grid in an instant. The system, unable to compensate for that sudden loss, collapsed. The entire Hydro-Quebec grid went dark, the whole of it, in less than 90 seconds, in less than the time it takes to read this paragraph aloud. 6 million people woke that morning to darkness. The blackout lasted 9 hours. In the United States, the New England power pool simultaneously lost 1,410 megawatts. The New York power pool lost 150 megawatts. At the Salem nuclear power plant in southern New Jersey, a generator step-up transformer overheated and failed. A failure that would not become apparent for months, only revealing itself through the slow signs of internal core damage. Across the continental United States, more than 200 separate grid disturbances were logged within minutes of the storm's peak. Researchers who have reviewed the railway records from Russia found that the same storm caused automated signaling systems on the Gorky Railway to report false blockages of track sections for intervals of 3 to 4 hours repeatedly. David Boatler, head of the Space Weather Group at Natural Resources Canada, has described March 1989 as the biggest geomagnetic storm of the space age, and the archetypal disturbance for understanding how solar activity can cause blackouts. That word, archetypal, carries weight. It means the field of grid vulnerability analysis was born from that event. The engineering response to that event, the conferences, the hardening studies, the protective relay upgrades, were all responses to something that had already destroyed a functioning modern power system in under 2 minutes. And the geomagnetic storm that did it was classified, by the measures available at the time, as a G4 to G5 level event at the top of the scale. What is occurring today sits at G1, with G2 possible. The distance between G1 and G5 is not merely a numerical distance, it represents orders of magnitude in induced current intensity and the area of infrastructure at risk. But the distance between G1 and G5 is also the distance the Sun crossed in 1989 without enough warning for any operator to prepare. The question is not whether the current event will reach those levels. The question is whether the next compound event, the next convergence of a fast coronal hole stream, a direct CME impact, and a southward-oriented interplanetary magnetic field, will. And when it does, the system it encounters will be more complex, more digitized, and more dependent on electromagnetic stability than the system that failed in Quebec in 1989. Think about what Montreal looks like on a winter morning when the power goes out. Now think about it lasting not 9 hours, but 9 days. Or 9 weeks in a scenario where multiple large transformers require replacement rather than reset. Montreal has a population of approximately 1 million people in the city proper, nearly 3 million in the greater metropolitan area. In March, when the 1989 storm struck, the overnight temperatures in Quebec regularly dropped below -15 degrees Celsius. Heat in Quebec runs on electricity. Hospitals in Quebec run on electricity. In 1989, the blackout lasted 9 hours and people managed, the backup systems held, the hospitals stayed on generators. But the engineering literature that followed 1989 is explicit about one thing. If the storm had been slightly more intense, if the induced currents had been slightly higher, if the protective relays had not tripped quickly enough to limit transformer core saturation, the damage would not have been a 9-hour event. It would have been a 9-month event because the transformers themselves would have required replacement, and replacement cannot happen in 9 hours or 9 days. It cannot happen in 9 weeks. The lead time for a large high-voltage transformer is measured in years. The United States currently holds a limited strategic reserve of recovery transformers, but that reserve, documented by the Department of Energy, is designed to address localized, weather-related grid damage, not a continent-scale simultaneous failure event, the gap between what the reserve can absorb and what a Carrington class event would demand is not a gap that can be closed by logistics. It is a gap that would be measured in darkness and cold and the cascading failure of every system that depends on continuous electrical power to sustain human life. Now move from Quebec to the present map. Think of the families in Troms, Norway, a city of approximately 77,000 people positioned inside the aurora oval, a zone where geomagnetically induced currents are strongest because the magnetosphere above it is perpetually distorted by the solar wind. Think of the fishing communities in northern Iceland, where undersea power cable infrastructure connects isolated populations to the main grid, and where the beautiful auroras that light the sky on any given night are visible precisely because those people live inside the most electromagnetically active zone on the surface of the planet. What would a person living in Troms ask if they had access to the same NOAA monitoring data that space weather engineers are reading today? They would ask exactly what any informed person asks when the instruments show what they currently show. At what level does the interesting become the dangerous, and how much warning will we have when the boundary is crossed? The honest answer, the one that scientists choose their language carefully around, is that the warning time between detecting a major CME at the Discover satellite at the L1 Lagrange point, roughly 1.5 million kilometers from Earth, and the moment that CME's shock hits the magnetosphere is approximately 15 to 60 minutes, 15 minutes for a direct, fast CME. That is the window between the last moment of normal operation and the beginning of whatever follows. And this connects to the second global system that the current solar activity is pressing against simultaneously, one that receives far less attention than the power grid, but carries its own category of cascading risk. The Global Navigation Satellite System, GPS, GLONASS, Galileo, Beidou, the full constellation of orbital positioning infrastructure that now underpins aviation navigation, maritime routing, financial transaction timestamping, cellular network synchronization, and precision agriculture, is exquisitely sensitive to the ionospheric disturbances that accompany geomagnetic storms. When a geomagnetic storm heats and expands the ionosphere, it creates density irregularities in the layer of atmosphere through which GPS signals travel. Those irregularities bend, delay, and scatter the signals. The positioning errors that result range from meters to tens of meters under moderate storm conditions, and can render GPS entirely unusable at high latitudes during severe events. Aircraft operating in polar routes, the Great Circle routes over the Arctic that connect North America to Asia and Europe, routes that carry enormous volumes of commercial aviation, are required to divert to lower latitudes when solar radiation storm and geomagnetic storm conditions exceed threshold levels. Airlines carry the operational cost of those diversions, measured in additional fuel burn, additional flight hours, and schedule disruption, as a standard space weather business risk. But the more subtle vulnerability is the one embedded in financial infrastructure. Every modern stock exchange, every high-frequency trading system, every bank transfer that is time-stamped and synchronized across global networks uses GPS timing signals as its reference clock. GPS timing errors during a geomagnetic storm do not announce themselves. They propagate silently through financial infrastructure as synchronization drift, and the consequences of unsynchronized financial timestamps are not abstract. They are the kind of errors that trigger cascading automated responses in systems designed to protect against exactly this kind of anomaly by shutting down. Markets pause, transactions halt, settlement systems freeze. And all of this occurs not because of any human decision or cyber attack, but because a star 150 million kilometers away disturbed the magnetic field of a planet for a few hours in the middle of a Thursday afternoon. The third system, the one that the long view of planetary behavior demands be mentioned, is the one almost no one discusses when the conversation is about solar storms, because it operates on a timescale that feels geological rather than immediate. Earth's magnetic field is itself in a state of gradual change. The magnetic North Pole has been migrating at an accelerating rate for the past century, moving from northern Canada toward Siberia at speeds that have reached more than 50 kilometers per year in recent decades. The South Atlantic anomaly, a region of weakened magnetic field over the South Atlantic and southern South America, where the inner Van Allen radiation belt dips closest to Earth's surface, has been expanding. These changes in the geometry and intensity of Earth's own magnetic shield mean that the same solar wind pressure that produces a given level of geomagnetic disturbance at one point in Earth's magnetic history may produce a larger disturbance as the field continues to weaken. This is not a near-term catastrophe. The field weakening is slow by human timescales, but it is happening. And it means that the vulnerability baselines established by the events of 1989 and even 2024 are not static. They are trending in one direction. The planet's natural defense against the solar wind is gradually diminishing, and the solar wind is arriving today at 700 kilometers per second. Scientists choose their language carefully here, and that careful language is itself the warning. When researchers at the USGS publish assessments stating that a Carrington-class geomagnetic storm could adversely affect telecommunications and electric power transmission across the United States, particularly in the Midwest and East Coast, they are not projecting a science fiction scenario. They are describing a physical mechanism that has already operated at smaller scale, that they have measured in laboratory conditions, modeled in computational simulations, and observed in the behavior of transformers during every major geomagnetic storm since 1989. Swiss Re, the reinsurance company whose actuarial models exist to quantify the probability and cost of large-scale disasters, has estimated that 10% of all high-voltage transformers could be damaged during a geomagnetic storm equivalent in intensity to the Carrington Event, 10% of the high-voltage transformers. In North America's grid, on infrastructure where the replacement lead time is measured in years, the probability of a Carrington-level event occurring within any given 10-year window has been estimated by solar physicists at approximately 12%. That is not a remote probability. That is the same order of probability as a number of other hazards that command significant national preparedness infrastructure. And yet, the gap between the quantified risk and the actual preparedness investment remains, as documented in assessments published as recently as April 2026, one of the most significant mismatches in modern infrastructure policy on either side of the Atlantic. This has already happened once. The record of it is preserved in the ice cores of Greenland and Antarctica, where the isotopic signatures of major solar particle events appear as chemical layers in the ice, datable, measurable, and reaching back through centuries of solar behavior that predate any human instrument. The 774 to 775 AD event, documented in ice core data and confirmed in tree ring records from Japan and Germany, produced a carbon-14 spike in the atmosphere approximately 20 times larger than any event recorded in the modern instrumental era, implying a solar particle event of an intensity that makes the 1859 Carrington Event appear moderate. That event has no recorded human consequence because in 774 AD there were no high-voltage transmission lines, no GPS satellites, no cellular networks, no automated financial markets. There was only a planet hit by an extraordinary output of solar energy and a sky that would have burned with auroras visible at the equator, and then the ordinary continuation of human life in a world where the infrastructure was biological rather than electromagnetic. The infrastructure of 2026 is not biological. It is copper and silicon and fiber optic cable and software. And it was built, almost entirely, during the 70-year window between the end of World War II and the present, a window of solar activity that has been, by the standards of the geological record, relatively quiet. Relatively quiet. Those two words carry the weight of everything that follows. Because today is May 18th, 2026, and the transequatorial coronal hole is still open, still facing Earth, still streaming at 700 kilometers per second. The CME from AR4436's M1, 9 flare is still in transit. The KP index is at 5, and the G1 storm conditions are confirmed. The aurora tonight, if skies are clear, will be visible to observers in Seattle, in Minneapolis, in Edinburgh, in cities where the northern lights are not typically part of the evening sky. The lights themselves are beautiful. They always are. They have always been beautiful. But what they represent is the visible signature of charged particles pouring through a gap in Earth's magnetic shield and interacting with nitrogen and oxygen in the upper atmosphere. The same interaction that, at the ground level where the long conductors of civilization run, is silently inducing currents into the copper veins of the grid. NOAA's SWFO L1 observatory, which successfully entered its final operational position at the L1 Lagrange point on January 23, 2026, is watching. NASA's Solar Dynamics Observatory is watching. Space Weather Live's automated KP monitoring systems are watching. The entire global infrastructure of solar observation, assembled over decades at extraordinary cost and maintained by engineers and scientists at NOAA, NASA, ESA, and a dozen national space agencies, exists precisely to watch for this. And what all of that watching has produced, as of this morning, is a confirmed geomagnetic storm, a CME in transit, active regions still capable of producing additional flares, and a solar cycle that has already exceeded every forecast for its intensity. The monitoring is in place, the detection is possible, but prediction, true prediction, the kind that would allow a grid operator to take a transformer offline before the induced current reaches it, the kind that would allow an airline to divert before the GPS signal degrades, the kind that would allow a hospital to activate backup power before the main feed fails. That prediction remains constrained to a window of 15 to 60 minutes between the DS-COVR satellite's detection of an incoming CME shock and the moment that shock meets the magnetosphere. 15 minutes is not nothing. It is better than zero. But it is also not enough time to safely de-energize a major transmission corridor, which requires coordinated action across multiple operators, regulatory notification, and a sequence of switching operations that grid engineers routinely describe as requiring hours, not minutes, to execute safely. The question is not whether, the question is when. And on the morning of May 18th, 2026, the instruments are showing the current. The aurora is beginning to glow. And somewhere between the sun that is 150 million kilometers away and the transformer in a field outside of a city that has no idea this conversation is happening, the electrons are already moving. On September 1st, 1859, British astronomer Richard Carrington sat at his telescope and watched a brilliant white flare erupt from the surface of the sun. He sketched it. He recorded the time. He published his observation. 17 hours later, the CME his flare had produced hit Earth's magnetic field with an intensity that has not been equaled in the 167 years since. Telegraph operators across North America and Europe reported sparks leaping from their equipment. Telegraph paper caught fire in stations where the batteries had been disconnected. The aurora was seen in the Caribbean. Miners in the Rocky Mountains woke at 1 in the morning, certain the sun had risen early. The entire electrical infrastructure of 1859, a network of telegraph wires strung across continents, was struck simultaneously and failed simultaneously, and then, within days, largely recovered, because the infrastructure of 1859 could recover. It was wire. Wire can be repaired. Wire does not require a 4-year manufacturing lead time. The infrastructure of 2026 cannot say the same. The sun does not know what year it is. The sun does not know that $9 trillion in unprotected infrastructure now lies in the path of the solar wind. The sun does not know that the transformers in the substations outside of Toronto, and Chicago, and Frankfurt, and Mumbai are designed for alternating current and are vulnerable in a way that was not true of telegraph wire. The sun is simply doing what it has always done, burning, convecting, erupting, and sending its output outward in all directions at 700 kilometers per second, the same speed it reached yesterday and the same speed it will reach tomorrow, in a cycle of activity that has been running for 6 billion years without reference to the things we have built in the last 100. The coronal hole is still open, the solar wind is still arriving, and the planet that has always survived what the sun sends, because for all of its history before the last 100 years, survival required nothing more sophisticated than standing on the ground, is now threaded end to end with conductors that the sun has learned without intending to, exactly how to disturb,